Notes on absolute age. Absolute age, when roundabout age isn't good enough, like in relative dating, but we need the actual date of the event. We can use tree rings and varves. You all should know that every year that a tree is alive, it adds an extra layer to itself. And if you were to cut down a tree, you can see these different rings and you can count them up and figure out how old the tree was. And then also radioactive decay, and that's the main thing that we're going to focus on. If you have something that's radioactive, as the radioactivity sort of breaks down and decays, it changes to a different element, and then you can measure the different amounts of each element and figure out how long the material has been breaking down. Most rocks contain elements that are radioactive. Since these elements give off particles and energy, they will eventually form new non-radioactive elements. By comparing the amount of radioactive and non-radioactive elements, scientists can predict the absolute age of a specific rock. So get an actual numeric age. That's the big thing to know about absolute. It gives you an actual age, whereas relative just tells you older or younger. And an example here is uranium. It's commonly found in rocks. Uranium-238 will decay to form uranium-234. So it releases 2 protons and 2 neutrons. It will eventually decay all the way to produce lead-206. So uranium-238 is the parent element. It's what we start out with. Before someone can have children, you've got to have the parent. And then the child, in this case, is called the daughter. What it breaks down into is lead-206. So whatever you start with is the parent. What it breaks down into is the daughter. And a half-life. This can be kind of confusing. The decay of uranium-238 to lead-206 is a very slow process. The rate of decay is constant, though. It takes 4.5 billion years for half of uranium-238 to decay. So a half-life is however long it takes half of the radioactive material to decay. The more lead-206 in a rock, the older it will be, because that means it's been breaking down longer. So you've got less uranium, more lead, the older that rock is. And then here's a picture of a trilobite. Carbon dating. C14 is a radioactive element found in all living things. When plant or animals die, carbon-14 decays to form nitrogen-14. The half-life of carbon-14 is about 5,730 years. And that's going to be real important when we get down to that big chart on your notes. So here we've got a living organism. You're collecting carbon-14, adding carbon-14 to yourself. As much as you're alive, you got carbon-14 for as long as you're alive. And then as soon as that organism dies, you don't have any more new carbon-14. So you're not building anything up anymore. As you start to break down, that carbon-14 changes into nitrogen-14. So 5,730 years later, you've lost half of that carbon-14. So you're half carbon-14 and half nitrogen-14. And then 5,730 years later, which is now 11,460 years later, you've got 25% carbon-14 and now 75% nitrogen-14. So this is actually what we're going to do, is fill in the chart on your notes. And you can start your chart here, because at year 0, the organism has just died. So you're at 100% carbon-14, no nitrogen-14. And then 5,730 years later, you're at 50%. and that's half, because it's a half-life. And then on the next line, you've got 11,460 years later, you're at 25%, so that's a quarter of carbon-14. So all you're doing is adding 5,730 years for every half-life, and then you're going to divide by 2. So if you start out at 100%, now we've got 50%. Then it's going to go down to 25%, and then half of 25% is 12.5. And then you just continue to divide by half until we get down to almost nothing. But you're never going to get 0% carbon. It just doesn't work out that way. So make sure you have those first couple of lines filled in on your notes, and then when we come back to class, I'll actually go through with you and fill in the chart in case you've gotten confused about any of this.